Hello, welcome back to my channel on quantum computing. I'm Kadreshan. 3 weeks ago, we had a lot of stories, right, on quantum Google's quantum algorithm, Echo's algorithm in a Willow chip. It's a great achievement, a breakthrough and all. But what exactly has been done, I couldn't get. So I thought of doing some bit of research. So I got some details. That's what I'm going to share with you on this video, so that from a common man's perspective what has been done and how it is going to be useful, right? So we'll just get an introduction about the quantum computer, what Google has, and then the study's relevance to a real life problem and how it is related to NMR studies. Okay, and the algorithm details, we don't go very detailed stuff into the algorithm because so much is not available, but we get a rough idea about what has been done in this echoes algorithm and is there any real advantage of these studies, then is there any limitation of this study. So all these points we'll try to cover in this video. Okay, so these are all some of the headlines I picked from the media. Google's Willow chip just made quantum history with quantum echoes. So one thing is clear that their algorithm name is echoes, and they ran this algorithm in their Willow chip, right? Which I have, another video sometimes back, right, on the Willow chip's capability. Google's new quantum computing breakthrough just shocked the world. I don't know why somebody got shocked, but certainly it's a breakthrough. Google's Willow quantum chip just delivered a verifiable quantum advantage. So this is an important point, which anyway we are going to see later in this video. Verifiable and quantum advantage. Google's 105 qubit Willow chip achieves first ever verifiable quantum advantage. So we know that the Willow chip has got 105 qubits, but for this study I understand that they used 103 only. Google's quantum chip just broke physics. Scientists are freaking out. I mean, it's a funny title. I don't know how physics was broken, but anyway, just for fun, Google's new computer is 13,000 times faster than all supercomputers. This is an interesting point. We will see with some more details later. The quantum echoes algorithm breakthrough offers a path toward unprecedented scientific discoveries and analysis. So this is very important because this is where you find an application for the entire study. Okay. So on your right, you see Sundar, CEO of Google and its parent company, along with the quantum computer of Google. And this is the Willow chip placed inside this quantum computer. And this has got 105 qubits in it. So we'll start with the relevance to your real life problem. Okay, so at the outset, this study helps to do molecular modeling. Okay, so Google demonstrated the technique in a proof of principle experiment to act as a molecular ruler. So you will see what is molecular ruler to measure the geometry of small molecules with results that match the traditional nuclear magnetic resonance techniques. Okay, so this NMR technique has been used by scientists to understand the molecular property, how the atoms are bonded together. Okay, so at its core, it uses powerful magnets and radio frequency pulses to study the magnetic spins of atomic nuclei in a molecule. By measuring the way the spins affect each other, scientists can map the molecular precise 3D structure acting as a molecular ruler. I mean, that is the intention, that is theoretical, but I believe practically it's still not possible, okay? Because when the two atoms are far away, it's very difficult to study their interactions. Again, I'm not a physicist, okay? Sorry, my apologies if I make some mistakes about the NMR study. NMR echo. So this is an important thing. In NMR, scientists use a sequence of RF pulses to intentionally cause the nucleus spins to get out of sync. So take a molecule, apply some RF pulses, and then create some chaotic situation. Then apply a reversal, and then they try to undo in some steps, 90-degree and 180-degree pulses, to make them all refocus and produce a strong, clear spin echo. Okay, so when they do that, they get some information about the molecule. So that's what they are interested in, right? The echo measurement effectively cancels out noise and inhomogeneities, isolating the chemical information they want. So they have to formulate this experiment such that they get the required information between the atoms. I mean, the interactions between the atoms or the spins of the atoms. Okay. The primary application of developing new and improved molecular ruler techniques is to obtain quantitative, highly accurate distance distributions. That's why it's called ruler. Okay. What is the distance between different atoms in a molecule? Okay. And potential applications include distinguish between different structural models for a protein or nucleic acid. Okay, protein folding can be studied, how to develop a new drug, and how our body absorbs that drug, how to come out with new materials, material science and electrochemistry that will help us to create a more powerful and green batteries. Okay, now I hope you got the relevance. Okay, so but the question, okay, we have an experimental setup, why do you want to do it? But experimental setup involves a lot of cost and time. Okay, and still it is not accurate. So it's, if we can do this study in a simulated environment, that will save a lot of time for the scientist, and it will save a lot of money also for that. That is where Google's algorithm will help. So what are the steps involved? So first, the experimented that demonstrated verifiable quantum advantage. Okay, so this is important. Verifiable quantum advantage used 103 qubits in the overall forward and backward evolution sequences. So what is forward and backward? We will see it subsequently. So scientists send a carefully prepared quantum signal into the system. So this is the structure of the Willow chip. Okay, the system gets messy, information spreads out and scrambles like dropping a stone in a pond. Okay, as the gates are applied, the initial state evolves into a complicated superposition where the state of any one qubit is intrinsically linked to the states of many others. Okay, the term chaotic, or more formally highly scrambled, is used because the information from the initial state quickly spreads out across the entire 103 qubit system. The final state is an extremely complex superposition of 2 to the power of 103 possible basis states, right? So you have so much complex state which got generated in the process. Next comes the clever part. The scientists use a special trick to reverse the process. Okay, they threw the stone. Now they want to undo the effect. Okay, like magically sucking the ripples back to the center of the pond. The genius of the quantum echoes, which measures the out of time order or OTOC, is that it introduced a tiny perturbation between the forward and backward evolution. So when I read this kind of statements, I really didn't get full of it, but actually it is a very simple process. Okay, for a quantum software engineer, 103 qubits are all in ground state or zero, get zero state, right? So they prepared set of gates with single qubit and 2 qubits. We can, put together, we can call them as a unitary matrix. We know that, right? They applied the gates, then they did a small perturbation. They took one qubit and applied another gate. So actually with that, it affected the whole 103 qubits, okay? And then they try to undo what has been done. U dagger, they applied the unitary matrix, okay? If this was not applied, what we would have got? All the qubits would have gone to ground state or zero state. But because of this one particular disturbance or perturbation, you got some valuable information called OTOC, okay? So you carefully design the U and B, you get echo of the system behavior, okay? The complex relationship you get out of it. So the imperfect rewind, because of this, otherwise it would have been perfect rewind, we would not have got anything. The imperfect rewind causes the two paths, forward and backward, to interfere with each other. This interference is constructive, meaning the correct signal from the perturbation gets amplified, while the errors and noise tend to cancel out. This is a good thing. This is one of the novel idea Google brought into this study. The resulting measurable signal is the echo. Okay, so I want to I'll build my qubits or unitary matrix to represent a molecule, and I'll create a perturbation in a molecule, or in a qubit. Then I do apply U dagger. I get the information about the relationship. Okay, the echo comes out. Got it? So it's a very simple step only. But how to generate that is the domain knowledge we need. Okay. Continuing on the algorithm. This controlled interference is the physical phenomenon that is impossible for classical computers, okay, to simulate efficiently, and that is the key for both speed up and verifiability of the result. Okay, so later also we will see the speed about these 2 points. When they reverse it, they get a strong, clear quantum echo. This echo reveals how the quantum system behaved. What is the relationship between the elements of the system? Okay. Google, along with UC Berkeley, simulated two molecules, one with 15 atoms and another with 20 atoms, and they obtained perfect result matching NMR data. Okay, again, you should remember the output, what we measure at the end of all the operations, U, B, U dagger, they are not exactly representing the NMR data, but they can be correlated. Okay, similarity between Google echoes and the NMR echo. Google's quantum echoes algorithm is the quantum mechanical equivalent of spin echo. Okay, so there also we got the information. So here also about the molecules. Here also you will be getting the similar data about the molecule what we are simulating. Okay, the qubits on the Willow chip act as the coupled nuclear spins in a molecule. Okay, so we get the qubits, then we apply U dagger. They represent now the nuclear spins in a molecule. Then we apply the perturbation. The whole interaction gets disturbed. Then you try to apply U dagger, and finally the state what you get. And when you make a measurement, you get information about the relationship between the the elements of the molecules. Okay, the nuclear spins in a molecule. The forward evolution is analogous to the time period where the nuclear spins naturally evolve and scramble. The time reversal is analogous to the specific RF pulses we use, right? 90 degrees and 180 degrees. Used in NMR to refocus the spins and create the echo. The OTOC measurement effectively measures the coupling strength between the qubits, which is directly translatable to the distance and strength of interaction between the atoms in a real molecule, the ruler point, right? Now you got why it's called echo Google algorithm, because it uh, truly represents NMR echo. Okay, and quantum supremacy. This is what we are interested as a quantum software engineer, right? So qubit stores the complex state naturally. Okay, the qubit state, but requires in a classical computer, if you want to do, you need storing 2 to the power of n complex number, right? And for 103 qubits, it's almost impossible, right? So much memory is required. Core difficulty, many body interference. So once we apply U gate, it creates a very complex superposition of qubits. You need exponential scaling of memory. And then qubits interfere so naturally to find the answer in a single shot. But here you need to calculate and track each and every possibility. 2 to the power of 103 possibilities to simulate seat interference. So people estimated it will take 3.2 years of an exact simulation. They have not done it, but it's an estimation. So how did they arrive at? So number of flops required. For example, you can see here we have 103 qubits. So represented by a matrix of 2 to the power of n into 2 to the power of n. Such a big matrix. And when you apply a gate, you have to multiply that by a vector of 2 to the power of n. You can see complex. That is just to apply one gate on one qubit. So now you have so many gates, and there are 2 qubit gates. So they made an estimation, okay, like number of flops which are required, and how much time a supercomputer takes, and that's how they arrived at 3.2 years. Whereas this is practical time they have spent. So okay, so the speed 13,000. So how we got that number? It's from these two numbers: 3.2 years into 365 days in a year into 24 hours in a day divided by 2.1 hours. It will roughly transform to 13,000. Okay. This will translate into true economic advantage, time and money for solving real life problems, right? And it's verifiable. So this is an important point. The algorithm measures a single fixed physical quantity always whenever we do many number of. So repeatability, that is what they call it as verifiable. It's not only it's repeatable or in this it can be repeated on any quantum computer of similar caliber to get the same answer. Okay, so that is the new thing. A verifiable term has come into quantum computing. So why 2.1 hours? Because we know that gates are executed in microseconds or nanoseconds. That's true. But requirement for statistical averaging, I mean, when we write quantum computing code, we do many number of times. I believe they have done billions of times to get the right answer. And they used quite a deep circuit, 40 circuit cycles, and around 1002 qubit gates were used. In addition, error mitigation and calibration and readout time pushes the total experimental runtime into 2.1 hours. Okay, but still it gives us 13,000 times speed up, right? Okay, is there any limitation? Yes, because with this algorithm tomorrow we cannot develop a new drag. So what are the limitations? First, the qubit need. The experiment used 103 qubits to successfully model the information providing in a chaotic quantum system. It's good, but this 103 qubit scale was sufficient to model small molecules like toluene, a 15 atom molecule. Okay, to solve the killer applications like designing a new blockbuster drug or a revolutionary battery material, we may require thousands or millions of physical qubits, depending on the quality of the qubits, right? To construct hundreds of reliable error corrected logical qubits. So We don't have enough number of qubits with the present day technology. Noise and decoherence problem. Willow chip is an excellent chip. Okay, Google has done number of improvements on these two aspects, but still it's a NISQ device, meaning noisy intermediate scale quantum. It has noise and its median 2 qubit gate error is still around 0.15%. This is a huge achievement, but still it has some error. Without error correction, a long calculation would quickly become meaningless due to decoherence. Okay, so when will these limitations be overcome? Oh, well, the algorithm proves capability now, so it's proven. It's widespread, but it's widespread disruptive application in medicine or material development is expected to become viable within next 5 years. Again, it's not in our hands; it's in the hands of quantum hardware manufacturers like Google, IBM, Amazon, Quantinum, and there are many more companies who are doing that. Okay, so hopefully they'll be able to do within 5 years. All right, a reference you will get plenty. I just put for sample one video and one blog from Google. Thanks for watching this video. See you soon in another video. Bye.